Hi, my name is Robert Ahern, and I'm a senior at Vanderbilt University, and I'm studying biomedical engineering. Aside from VSVS, I work at the Children's Hospital.
I'm Kevin. I'm also a senior at Vanderbilt, and I'm studying biology and MHS. Aside from VSVS, I'm also involved in Vanderbilt GMA and VEMS, and I work in a research lab. And today we'll be teaching you a lesson titled Conduction, Convection, and Radiation. Hope you guys enjoy.
So a big aspect of conduction, convection, and radiation is temperature. Temperature is usually thought of as a scientific measure of how hot or cold something is. However, how hot or cold something is determined by the average kinetic energy of the molecules in a substance. So temperature is also a measure of that as well. Let's consider what happens when we add ice to hot tea. The ice melts and the energy from the tea is transferred to the ice. This transfer of energy is called heat.
Alright, so if you guys have seen things like mood rings and strip thermometers and other things that basically change color with temperature, that's what we'll be looking at next. So what I have here are some cool little things called liquid crystal temperature sensors. So they basically change color depending on the temperature of whatever's touching it. So before we get into this, some rules to go over when using these temperature sensors. Make sure the sensors are not placed in the sun or near a heat source. Always hold the strips using a clear laminated part, so not the actual crystal black part. Make sure that your hands are on the kind of border. And also do not touch the liquid crystal unless instructed to do so. Alright, so now we'll move on to kind of interacting with the temperature sensor and learning more about it. You'll notice that I've put it on top of a white foam pad. That is to insulate it, to make sure that it's not getting any external temperature influences. So what we're going to do is put 3 fingertips on the surface of the liquid crystal, and we're going to leave that there for 15 seconds. Alright, now that it's been about 15 seconds, I'm going to lift my fingers off, and we'll notice that the color dramatically changed. It looks like about a greenish on the inside, and on the outside it looks about like reddish, orangish. So we notice that 1, the color of the sensor changes, and 2, the color changes spread out from the center of the finger, and also the color changes as it spreads. So we have a variety of colors there. Alright, so now that we've gotten to mess around with the liquid crystal temperature sensors a little bit, let's talk about what we saw and why we saw that. So when I lifted my finger off of this sensor, you notice that the colors range anywhere from a bluish green kind of tint to black. So what we saw there was the color indication. So in order from coolest to warmest, you have black, yellow, green, and blue. So it made sense that blue was at the center because that's where my finger was most directly contacting the temperature sensor, and that's where most of the heat from my finger was being transferred to the temperature sensor. And this transfer of heat through direct contact is something we call conduction. Alright, so let's discuss the concept of conduction a little bit more through our liquid crystal temperature sensors. So as we discussed before, these liquid crystals are sensitive to temperature, and they will sort of change color according to what temperature that. They do this by separating visible light into different colors according to the temperature of the crystal, with black being the coolest. So if I'm transferring thermal energy from my finger onto the temperature sensor, you can notice that it changes color, ranging from blue out as we discussed before. However, after I lift my finger off, you will notice that the temperature the color is slowly fading a little bit, and it's kind of changing color from blue to green, and also the size of that color change is shrinking. So that is evidence of the heat energy that I transferred onto the temperature sensor transferring from that sensor onto the foam pad. So we're just looking at how heat has a tendency to flow from the warmer to the cold here.
Thank you, Kevin. So now we're going to look at how energy is transferred. Thermal energy is transferred by heat. Heat always flows from a hotter object to one that is cooler. In this case, your body is warmer than room temperature, and heat flows from your finger to the sensor. So let's think about what are the different ways thermal energy is transferred. I'll give you a hint. It's the title of the lesson. Conduction, convection, and radiation. Now we're going to see how conduction, convection, and radiation are used with our little liquid crystal sensors. So the first case we're going to look at is radiation. Radiation is the transfer of energy by electromagnetic waves such as light, UV, infrared, and X-rays. So let's think about some different sources that transfer heat by radiation. Off the top of my head, I can think about the sun, a fire, a bar heater, and even light bulbs. Radiation does not rely upon any contact between the heat source and the heated object. Radiation can even be transferred through space where there's a vacuum, especially and this is seen in the case of the sun. We can feel heat from the sun or a fire even though we are not touching them and there is no air in space. Alright, and now we're going to demonstrate radiation with this here lamplight. So what we're going to do is we're going to take our sensor and we're going to place it about 5 to 10 inches away from the lamplight and we're going to turn it on. And as we wait, let's see how the lamplight isn't touching the sensor directly. There is air between the two. And what's going on is the electromagnetic waves from the lamplight are flowing out in every direction. Awesome. And as you can see, the heat crystal heated up. It changed color everywhere. Alright, so another way to visualize radiation is with this little thermometer right here. So what this does is, you press the measure button and it sends out an infrared laser beam and it comes back with a temperature of whatever it hits. So what I'm going to do first is take the temperature of my hand. As you can see, 89.5. And now what I'm going to do is I'm going to let the light source sit right here and heat up my hand real quick. Radiation. Radiation. And now I'm going to take the temperature of my hand. And as you can see, it kind of went up to 91 right there. So that's just another example of how radiation works.
Alright, so now we're going to move on to another form of heat transfer called convection. So to define convection simply, it is when an external heat source heats up either a gas or a liquid. In our case, we'll just be looking at the convection of air. And this causes the molecules of that gas or liquid to kind of space out and become less dense. Because it is less dense, it will now rise, whereas the cooler remaining air or gas or liquid will fall. So this causes a transfer of heat via how the warmer molecules rise and move up while the cooler molecules move down. So we'll be seeing this visualized by using 1, heat packs, and 2, our liquid crystal temperature sensors. Alright, so as I said before, we'll be using heat packs, our temperature sensors, to visualize convection. So we can activate the heat pack by pressing on this little metal bit inside it to disturb the liquid. And as you can see, it starts solidifying and I can instantaneously feel the heat coming from it. So I'm going to place it on my foam pad here, let it finish that. And while it's on that pad, if I put my hand above it, I can definitely feel heat emanating from the heat pack. So that's evidence of convection, as how the heat is being transferred through the air via warm molecules of air kind of rising. So we can also visualize this by using our temperature sensors. I want to make sure that I don't place it too close, but maybe a couple of inches away. All right, nothing yet. Let's try a little bit closer, maybe 2 centimeters away. And you can kind of see a little bit, pretty good amount of heat transfer. So that's kind of just evidence of how our air is being heated up via this heat pack, and it is rising through the air via convection. All right, so now we'll be going over the concept of conduction more in depth. So conduction is defined as the transfer of thermal energy between objects that are physically touching. So earlier we explored conduction from the transfer of heat energy from my finger to this liquid temperature sensor. So an interesting property of conduction is that some objects can be a poor thermal conductor and some objects can be good thermal conductors. So if If you think of good thermal conductors, you might think of metal. For example, the metal used in cooking pots, or where they transfer heat from the flame to whatever you have into the pot very effectively. If you think of poor thermal conductors, you might think of foam boards, stuff like this that we use to insulate the temperature sensors from any external sources of heat. All right, so now we're going to explore the concept of different objects having different thermal conductivity properties a little more. So here I have a foam board, and on top of that I have a strip of copper, a strip of wood, and a strip of iron. And on top of that we have the liquid crystal temperature sensors that we have been using, and also a heat pack. So basically what we'll be looking at here is how well can these three different materials conduct heat compared to each other. And we'll be doing this by first activating the heat pack. Wait for that to activate. And once it is fully activated, we're just going to go ahead and put it right on top, or a little bit away. Make sure that it's a little bit spaced away from the temperature sensors. And basically we're just going to see how well can these three different materials conduct the heat. We're going to let this run for a couple minutes, so I'll be right back. All right, and that's been a couple minutes. I've let the heat kind of transfer as fully as it can, and we can see that if we take this heat pack off, on the right side we had the copper. It's definitely had the most color change, so we can conclusively say that copper is probably the best heat conductor out of the three. Move on to wood. You can see it's barely moved. The color has barely changed a little bit up the strip, so we can maybe say that wood is not a great thermal conductor. And lastly, we have iron, somewhere in between the two, where it's definitely changed, but it hasn't changed to the extent that copper did. So this is basically just a visual demonstration of how three different objects have different thermal conductivity properties.
All right, so now we're going to observe ice on these two different black boxes. First, put some ice on this one. Observe how fast it melts. It looks like it's not melting at all. All right, we're going to sit some on the other one. Wow, look at that melt. It's going so fast compared to the other one. So this is just an example of how color doesn't necessarily matter as much as what the material is made of for conduction. Now we're going to try to measure conduction even further with different materials over here, with these three blocks. Alright, so now we're going to place the blocks in order of hottest to coldest. So we're going to start on the right here. Alright, the styrofoam block it's not too hot, it's not too cold, it's kind of around room temperature, so we're going to leave it there. Next up, we're going to take the stainless steel and we're going to touch it. Ooh, that's very cold. So what we're going to do is we're going to keep that there for now until we feel the wood block. Alright, so the wood block is warmer than the steel but colder than the styrofoam. So what we're going to do is we're going to change it up the order. Alright, so steel like on the left, wood in the middle, styrofoam on the right. Alright, so now we're going to use our strip thermometers to record the temperature of each block. So let's start over here. On the styrofoam, it looks like 70 is about the temperature of the styrofoam. So the dark blue number is the one that is closest to temperature of the object it's touching. Next up, we got the wooden block. And let's wait a couple seconds. Wooden block looks exactly the same, close to 70. And now we're going to move over to the steel. And yep, similar. Steel is 70 as well. So with this knowledge that all three blocks are roughly about the same temperature, what do you think is going to happen if I put ice on each one of them? Well, let's find out. So I'm going to put a little bit of ice on each one, so some on the styrofoam, some on the wood, and some on the aluminum. So let's go over to the right. So the one that felt the warmest as well as being the least cool is the styrofoam, and it looks like the ice isn't melting at all. In the middle we got the wood, which was the middle of the ground, and the ice is melting but not too fast. And if we look over at aluminum, the ice is already melted, it's already water. So now what we're going to do is we're going to remove the ice. Let's measure the temperature again. All right, so it looks like styrofoam did go down a little bit to 68. The wood one looks also around 68, but it looks like the blue is also moving towards 66. So it is a little cooler than the styrofoam. And then let's put it on the ice. Yeah, the aluminum. And yeah, as you look at that, the aluminum is going all the way down. It's dropping fast. You might even go down to 64, 62 at this rate. So why did the ice on the metal melt so fast? Especially faster than the wood and the styrofoam? Well, the truth of the matter is that metal is a good conductor. It transfers heat from it to the ice faster than the other two materials. All right, so now let's go over some results. Why did the metal square feel cooler than the others when the actual temperature was the same? Well, the cold square is conducting heat away from the hand, so it is actually the hand that is cooling. Now let's also think about which was the best conductor. The best conductor was obviously the aluminum square right here, because it was able to transfer heat away from the ice very fast, which caused it to melt. So which was the worst conductor? Well, that's the styrofoam right here, because the ice didn't really melt at all. And a bad conductor is known as an insulator, because it isn't able to conduct heat at all. It insulates. All right, so that's all we have for you guys today. I hope you learned about conduction, convection, and radiation.
More importantly than that, I hope you guys had fun and stay safe out there.
Bye, guys.
Bye-bye.